Hello everybody. In this video we're going to talk about the strategy of solutions or the steps that we should follow to solve the problems that involve molecular diffusion. And this strategy is important to be in mind because this is going to be the same procedure that we follow in all the problems that we face. And this is pretty helpful because this gives you a mind map of where you are gonna go, and what the information that you need at this stage of the solution. We know some information about the continuity equation. We know information about the boundary conditions. We know information about the special cases of the continuity equation, and this strategy of solution is the procedure that will let us put everything together and get something out of all these information. So the first thing, or the first important thing that you need to keep in mind and to always remember, is that the solution is based mainly on your understanding of the problem. We mentioned this earlier, and I want to repeat it, that the understanding of the problem is very, very, very important. It's going to let you translate the information that you know into proper equations. It's going to give you a better imagination of how the system works and what you need to get out of it, and it's going to give you some kind of evaluation of the output that you get. Is it logical or not? Does it make sense or it doesn't? So this is very, very, very important. So one thing that you can do after you read the problem well and understand the inputs well is to sketch it. So draw a simple sketch of the system. Draw the boundaries, where the diffusion starts, where it ends, where are or what are the dimensions, which is z equals 0, z equals l, or r equals 0, r equals r1, r equals r2. Whatever the dimension that you have, it's good to put them. If you have an axis of symmetry, you have to put it so that you can have a visual understanding of the system. It's also helpful to put any boundary information that you have. So let's say you have a surface where the concentration equals specific value. So if you put the value here, it's gonna be easier for you to link that this is a boundary condition. So it saves you time of going back and forth between the solution and the problem statement. So this is the first part of it, or the first step. The second is to write the assumptions, and these assumptions again are based on your understanding, and this is something that is important because you are going to build on it on the coming steps. So the assumptions are related to everything that you have. So if you have or you understand that your system is at a steady state, so you translate this into the time dependence term equals 0. If you know that it is the concentration is dependent on x and y only, so you know that it is not dependent on z. There is no reaction, then you put r equals 0. So anything that you understand from the problem statement, you can translate this into equations or into assumptions. So these assumptions are going to be translated later into equations, but you just put all the assumptions that you have written in points. So this is the second point. The third point is to write the differential equation in the proper coordinate system. So if it's also something important to know which coordinate systems is going to be the best to describe your system. So if it is Cartesian, if it's cylindrical, if it's spherical, this is gonna be good to understand or to choose. And then you can apply your assumptions, cancel the terms that are not applicable in your case. As I said, there is no reaction, put r equals 0. If there's steady state, put the time dependence equals 0, and so on. And then the next step is, I think till this point everything is kind of okay, but this equation is going to be in terms of NA. So the general equation that we have is it's del dot NA. So this is in terms of NA. So usually we need or we want to have the equation in terms of C, because the output that we are interested in is a concentration the concentration profile or whatever. So we write the definition of Na based on the information that we know from chapter 22, which is relative to I mean, is it a constant temperature or and pressure, or it's a variable temperature and pressure, if it's in moles, if it's in mass. So you have to write the proper definition of Na, and then we can simplify it as according to the assumptions that we have, and then we substitute in the differential equation with the Na form or the equation, and then solve the equation, of course using the boundary conditions and initial conditions, whatever. I understand that this is not easy to imagine or easy to grasp, and that's why this diagram might be easier. So again, it's the same steps after you draw the sketch of your system, after you put your assumptions and everything. So you start with the differential equation of mass transfer, and then you put your assumptions, and then you have a simplified differential equation of mass transfer after cancelling the zero terms, and then you get the diffusion mass transfer equation, which puts Na equals negative C dAB partial Y partial Z, whatever the equation that you have, and then you substitute with this equation in here, and then you can have more assumptions related to the flux equation, and then you get the differential equation in terms of C instead of N, and then with the boundary conditions and initial conditions you can integrate the equation and get the concentration profile. This is one route of the solution, and you see that you have just this from here, and this is in an addition to this. You can get this equation transferred into the concentration equation. In some other cases, this procedure is not the one that's the suitable procedure for the solution. Sometimes you need to go like this arrow and this way. So the reason we sometimes go in this direction is because in some cases, for instance, if you have a steady state with no reaction, unidimensional, then the equation will end up to be the flux equals zero, the dN by dZ equals zero. This is what you get, and this in this case the flux equals constant, and this is all what you can get from this equation. So you cannot get anything more out of it. So in this case you go this direction. So you know that flux is constant, so this is the information that you know, and then you start with this fixed equation, you integrate it, and then you get the form of Na, and then you integrate this is the same. I don't know why they did it twice, but anyway, so this goes directly to here. So this integrated form of the Na or omega A can be differentiated to get the concentration profile. I understand that it's still not clear and it's kind of confusing, you don't understand well, but this is something that we will understand more when we go to or solve some problems, and this is what we will do in the coming couple of videos. We will solve problems, and I'll be going back and forth between the solution and this diagram. I'll tell you now we are in this step, and then solve a couple of things in the problem, and then come back here. Now we finish this step and we are in the next step, and so on. So this is what I am going to be doing in the coming two videos. So I'll see you then, inshallah. Goodbye.